low mass, like 9.21, electron mass is 9.21 into 10 to the power minus 31 kg, and the proton mass is 1836 times 9.1, 10 to the power minus 50 minus 31 kg. So this kind of object has a very low mass, and when that kind of mass moves with a very high velocity, and that velocity is comparable to the velocity of the light, okay, that velocity is comparable to the velocity of the light, not equal to the velocity of the light, but comparable to the velocity of light. For example, say c is equal to 3 into 10 to the 8 meter per second, or the velocity of the object is say 1.8 into 10 to the power 7 meter per second. So that is comparable, okay, or 1.8 into 10 to the 8 meter per second, that is comparable, or 1.5 into 10 to the 8 meter per second, that is the velocity of the light by object is half of the velocity of the light, so comparable. So when the particle of very low mass and moves with the velocity comparable to the velocity of the light, that particle, in that kind of particle actually have a both particle nature and wave nature. Once that kind of particle can be defined, the mechanics of them can be defined both by particle nature and wave nature. This is called wave particle duality. Wave particle duality. That means the particle which are very low mass and moving at a very high velocity, then that particle can be defined as a particle, and it can also be defined as a wave. And you know that a particle nature is defined by P, and the wave nature is defined by lambda, and these two parameters is connected by relation P is equal to h by lambda. Okay, P is equal to h by lambda, or lambda is equal to h by P. Okay, so the equation 1 and equation 2 is similar, mathematically similar, but physics tells us a particle of momentum P can be converted as a wave of wavelength lambda, and equation 1 tells us the wave of wavelength lambda can be defined as a particle of momentum P. Okay, so this is wave particle duality, and that's this equation 1 or equation 2. Actually the equation 2 which actually convert the particle nature into wave nature. Okay, equation 2 which actually convert particle nature. This is the first introduction theory. The particle is converted as a wave. P is equal to lambda is equal to h by P. A particle of momentum P can be defined as a wavelength lambda. For example, if I do some calculations over here to understand this physics, suppose this is two plates they are having the potential difference say 100 or 1000 volt, okay, now 1 kilovolt. So these two plates have a potential difference 1 kilovolt. This plate is positive, this plate is negative. That means if you release an electron from here, which have a negative charge, okay, then that electron is attracted by this positive plate and move towards this plate, okay, and the movement can be defined as a wave, and the wavelength of the electron associated its motion easily calculated. The wavelength you can calculate easily the wavelength of the electron associated with its motion. How? Very simple. The potential difference between these two plates A and B is 1000 volt, means 1 kilovolt. So when an electron crossing this plate, the work done is equal to electron volt, means 1.6 into 10 to the 19 coulomb into 1000 volt. So coulomb volt is called joule. Okay, this is a calculation to understand these equations, Actually, after doing the calculation, you can easily understand. If de Broglie did not discover this formula, then maybe one of these groups, maybe Arko, maybe Shamadev, maybe Harshadip, easily calculate this formula. So W is equal to electron into volt, charge into potential difference. Charge is 1.6 times 19 coulomb. Volt is 1000 volt. This coulomb into volt gives us a joule because Q into V is work done is joule. And that work done is by default because this positive charge attracts the electron. That's why this is the motion of the electron is by the force. That's why by the force work done is converted into kinetic energy. Okay, so this is kinetic energy. That means half mv square is kinetic energy. That means later I will substitute the value. Now I just put this expression. So E into V. So this is the velocity. Half mv square is equal to electron into volt. So this work done, kinetic energy is given by E into V, charge into potential difference. So mv square, that's nothing but 2ev. So m square v square is nothing but 2emv. So this is the velocity and this is the potential difference. This v is the velocity, this v is the potential difference. What velocity? The velocity with which it hit the electron in this plate. Okay, mv square is equal to 2emv. So this is actually the momentum p square, that is 2emv. So P is the square root of 2emv. Therefore, lambda is nothing but h by P. So h by root over 2emv. This is the wavelength, lambda h by 2emv. Now putting the values, you can easily calculate the wavelength associated with the motion of the electron. Okay. So h is a Planck constant 6.624 into 10 to the power minus 34 divided by square root of 2 into e 1.6 times 10 to the power minus 19. That value. Okay, I just carry this value over here. Then m is 9.21 into 10 to the power minus 31 kg, the value of the mass of the electron. And then v I put v as 1000 volt. Okay, 1 kilovolt. So let's have calculation. 6.624 into 10 to the power 34, and this is 1.6 9.1. Okay, 2 into 1.6 into 9.1 into 1000 into 1000. Okay, and outside the square root, this is minus 19, this is minus 31, is minus 50, 10 to the power minus 50, square root into minus 50, we will get 10 to the minus 25. So this is 10 to the minus 25. And if you cancel this will become 10 to the minus 9. The 6.64 10 to the minus 9 by this much. Okay. So what would be your value? The calculation of the calculator. So this is 1.23 into 10 to the power minus 10 meter. So this is your lambda, 1.23 into 10 to the power minus 10 meter. So the wavelength is 1.23 Armstrong. That is more or less wavelength of the X-ray. Wavelength of X-ray. Okay, 1.23 Armstrong more or less. This electron now is now have a wave nature, and the wave associated with the motion of the electron is like a X-ray wave. Okay, so this is all about the de Broglie formula, de Broglie hypothesis. How this particle nature, that means electron motion, is defined by a wave. That wavelength of the wave is defined by the formula lambda is h by p. And when the electron is moving across this potential difference, having 100-volt potential difference, then the amount of work done by the field is given by work done is equal to charge into potential difference. And since the electron is moving against the by the force, because electron is moving towards the positive plate, and that work done by the force is converted into kinetic energy, and that kinetic energy is given by half mv square, and that half mv square is nothing but ev. And in doing the calculation for the process, you can easily calculate the wavelength associated with the electron, and putting all these values, you can easily find out the wavelength is approximately 1.23 angstrom. Actually, this is of the order of the wavelength of the X-ray. That means electron now is can be represented by the wave of having wavelength equal to the wavelength of the X-ray. So this is the wave nature of the electron. Okay, and the kinetic energy and momentum is the particle nature of the electron. Now, putting this from this expression, you can easily understand if the mass of the electron is very, if the mass of the object is very high, if the mass of the object is very high, okay, if the mass of the object is very high, then lambda is very low, okay. And so for a regular life where the Newton's law are applied, for example, the mass of the ball or mass of any others having mass 2 kg, 3 kg or half kg, that kind of mass have a very higher mass, because the electron have a very lower mass, minus 31 kg. And if you instead of putting these values, if you apply 1 kg, then you will see your wavelength will be of the order of 10 to the minus 34 or 10 to the minus 20, this kind of order. So this having wavelength, this kind of wavelength have no physical significance. Minus 20 have no physical significance. Actually, that's why the object having very higher mass cannot defined or cannot have any wave nature, because the wave associated with that very heavy mass is very low. That is of the order of very low, 10 to the minus 20 angstrom. You know, 10 to the minus 10 angstrom is 1 angstrom, 10 to the minus 10 meter is 1 angstrom. Then 10 to the minus 20 meter means 10 to the minus 10 angstrom. So this is very very low. It cannot be observed by any kind of instrument. So this is impossible, and there is no physical significance of the presence of the wave having this kind of very low length. That's why the mass of 2 kg, 1 kg, or you can say the very heavy mass is not associated with the wave. Okay, they have not associated with any wave of wavelength lambda. Or the mass of electron, like electron, proton, they are very low mass. Then their motions can be replaced by the wave, and they have a very significant value. For example, in this case, we got the wavelength 1.23 angstroms. That means it has some value, it has some physical significance, because we have the order of this wavelength is like X-ray. That means electron can be replaced by the electromagnetic wave of the order of X-rays. So this is the physical significance of the de Broglie hypothesis, and you can easily understand why the masses in our regular life cannot be replaced by the wavelength, but the masses like electron motions, proton motions can easily be replaced by the wave. This is how the first wave nature is introduced in the physics to actually define the motions of the electrons, protons, this kind of very low mass. Okay. Now, for the case of photon, photon is a particle which is not associated with any mass. Photon is a particle. Electromagnetic wave, which have wavelength lambda is equal to c by nu. Then, according to de Broglie, then this wave nature of the electromagnetic wave, can also be replaced by the particle nature. Okay, the wave nature of the electromagnetic wave can also be replaced By the particle nature, the particle nature represents the momentum. That means the wavelength of the electromagnetic wave is replaced by the particle nature or momentum. Also, you have to understand the momentum for the case of photon. Photon has no mass. Photon has no mass, but still it has momentum. Photon has no mass, still it has momentum. But how do you calculate the momentum of the photon? Very simple. The momentum P is h by lambda. This is the relation for the photon. Photon has a wave nature because photon is the electromagnetic wave. Photon is electromagnetic wave. Electromagnetic wave now defined by particle is called photon. Okay, electromagnetic wave is defined by particle which is called photon. How do you say electromagnetic wave is defined by a photon? Because de Broglie tells us any wave can be replaced by particle and any particle can be replaced by wave. So photon, electromagnetic wave, whichever wavelength, whichever wave nature, then according to de Broglie, it can also be replaced by particle, and the particle is called photon. Okay, although the particle is called photon, but still it has no mass. Okay, it has no mass, but although it can be replaced by particle nature. How? Using the de Broglie formula, momentum, that means the particle nature P is equal to h by lambda. P is equal to h by lambda. Okay. Now energy E is equal to h nu. This is the energy of the photon. E is equal to h nu. Okay. E is equal to h nu. Nu is equal to c by lambda. So h c by lambda. Now, so h by lambda, that is actually E by c. So that is equal to P. So this is the momentum. Okay, P is equal to h by lambda means E by c. So this is the relation from where you can easily calculate the momentum of the photon, either this equation or this equation. When the wavelength of the electromagnetic wave is given, then you can replace this formula. Using this formula, you can easily calculate the momentum of the photon, or if the energy of the electromagnetic wave is given, then using this formula, you can easily calculate the momentum of the photon. Okay. Although electron, for the case of electron, this formula is only applicable for the photon. Photon P is equal to E by C. This is not applicable for the particle. Okay. Although this formula is applicable for both the particle and the electromagnetic wave, but this formula is applicable for the photon, that means electromagnetic wave, because okay, for the case of particle, particle has a kinetic energy half mv square. This is the kinetic energy, and momentum P is equal to mv. So this is not actually equal to E by C or E by V. This is not equal to E by V. If we divide E by V, we have mv by 2. If we divide E by its velocity, we will get E by V means half mv square by V, we will get half mv. Not equal to momentum, but momentum by 2. So this formula is not applicable. That means momentum is equal to energy by velocity is not applicable by the particle. That means it's not applicable by the electron or proton, etc. particle type. But this formula is only applicable for the photon. Momentum photon field P is equal to energy by the velocity of the electromagnetic wave. That means C. So this formula is only used for the electromagnetic wave or photon, because the particle associated with the electromagnetic wave is called photon. So P is equal to E by C. This formula is only applicable for the photon. So E is equal to P C. So E square is equal to P square C square. So this is for photon. Okay, this is for photon. But for electron or very low means electron or any kind of particle type, this formula will be reduced to p square c square plus m naught square c to the 4. So this formula is modified to this. Okay, this is for photon and this is for electron or any kind of particle. Okay, E square is equal to P square C square, or E is equal to PC, and squaring you get E square is equal to P square C square. This is a formula for the photon, but this is the formula for electron, proton, etc. Okay, E square is equal to not only is equal to P square C square, but there is another term that is called M naught square C to the power 4. We can easily prove this formula. We can prove this formula if you want. Then I can prove case of photoelectric effect. In case of photoelectric effect, first Einstein used electromagnetic wave as particle. That particle is called photon. Okay, electromagnetic wave of wavelength lambda as particle which have momentum p is equal to h by lambda, energy E is equal to h. Okay, first Einstein introduced these formulas of integrability into his topic, which is called photoelectric effect. For this topic, he was awarded by the Nobel in 1905. So how? He takes alkali metal as a cathode. He connected this cathode to the negative terminal of the battery, and there is anode because it is connected to the positive terminal of the battery, and this exposed to the light. This cover, this is made of glass, so that easily the radiations penetrate this glass and fall into this cathode. Cathode, and this is anode. Why cathode? Because it is connected to the negative terminal of the battery, and this is anode because it is connected to the positive terminal of the battery. Okay, now I just modify this circuit. I connect a resistance over here, and okay, and I use a variable potential difference. I do it. So this is your resistance. To measure the current, I connect a ammeter over here. Ammeter. Okay. Now it exposed to the radiation. It exposed to the radiation. Like sun rays incident on this cathode of wavelength lambda and the energy h nu. So photon incident on the cathode. Photon incident on the cathode. Now this electromagnetic radiations can be defined by the photon. You can imagine this electromagnetic waves as a particle, and the particle is called a photon. The photon of energy h nu incident on the cathode, and on cathode there is a metal surface. There are number of electrons. It collides with the electrons on the surface of the cathode. Some of the electrons collide with the electrons. Some of the electrons collide with that photons. Get energy from the photon coming out from the cathode. Electron coming out from the cathode having different kinetic energies. That electron are attracted by the positive terminal and hence move to the anode, complete the path. As a result, current will flow through this wire in this direction, and we get current in the wire, the output circuit. Okay, when the electromagnetic radiations fall on the cathode means is an alkali metal, so metal surface, number of electrons are exist on the surface. These electrons collide with the electromagnetic radiations of photons, because the electromagnetic radiations now actually can be visualized as a particle. This is called photon. That photon and electron have are colliding each other. This is elastic collisions, so that electron gain energy from the photon, and hence the electron are coming out from the metal surface with some energies, variable kinetic energies are coming out from the metal surface, and as they are coming out from the metal surface, they are attracted by this positive terminal of the anode. So electron moving towards this side, reach the anode, complete the path. As a result, so when electron complete its path from cathode to anode, electron complete the path due to this positive terminal. This positive terminal is over here. This anode is actually positive. This is positive potential. So this positive potential anode attract the electron towards itself. So electron complete the path, reach the anode, so that electron complete its path, and we have current through the output, the resistance. This is how we get current. So the phenomena is like photon incident on the metal surface, electron ejected from the metal surface. This is called the emission of electron by photon. So emission of electron by photon. And that electron complete its path, and that means it when reach anode, then we get a current in the output, and that current is called photoelectric current. So that current is called photoelectric current. And the electron coming out from the metal surface due to the photon, and this is called photoelectric electron. Photoelectric electron. This is called photoelectric current. So this is the photoelectric effect. That means the photon incident on the metal surface emits electron, and if there is a positive potential surround the electron, then that potential attracts the electron. Electron comes out from the cathode, reach anode, so that we get current in the output circuit. That current is called photoelectric current, and the phenomena is called photoelectric effect. Okay. So what we get electron photon incident on the metal surface, and electron coming out from the metal surface. Okay, so the energy of the photon, that means h nu, is utilized in two purposes for this photoelectric effect. Number one, some of its energy is utilized to emit electron from the metal surface. Some of its energy utilized to emit electron. A part of the energy incident photon, that is, this is the energy of the incident photon or incident electromagnetic radiations. So H, this is the energy of the incident photon and incident electromagnetic radiations. Some of its energy is utilized to emit electron from the metal surface. Okay, and other part is utilized. Other part, if there is something remaining, then that remaining energy is associated with the electron as a kinetic energy. Okay, suppose for example, if the incident photon have energy 10, if the amount of energy utilized to emit the electron on the metal surface is 8, then remaining 2 is associated or is transformed as a kinetic energy of the electron emitted on the metal surface. Okay, if it is energy is 15, then amount of energy utilized to emit the electron on the metal surface is 8, then the remaining part, the 7, is associated with the electron as the kinetic energy. Okay, the amount of energy utilized to emit the electron from the metal surface is called the work function of the metal. The work function of the metal. Work function. This is the energy represented by W0. The kinetic energy is Ek. So Einstein gives an equation. Since the photon collide with the electron get complete energy from the photon, and that energy is utilized one part with that as a work function to coming out from the metal surface, and remaining portion as kinetic energy. So first is the energy of the photon, then it transferred to electron due to collision, means photon and electron collide with each other. So that energy of the associated photon 100% convert to the electron. Electron gains this much energy in h nu, and it utilizes this energy for two purposes. First, the major part is to is utilized to coming out from the metal surface, and second part is associated with his kinetic energy, Ek. Now this is a work function. So Einstein gives an equation with these parameters from the conservation energy, since it's elastic collision. So amount of energy associated the photon converted with the energy to the electron, and that energy utilized one part with the kinetic work function and other part as kinetic energy. So this equation is called Einstein photoelectric equation. Okay, this is Einstein photoelectric equation. So h nu work function plus kinetic energy, may say this is Ek. Now suppose you use radiations having more frequency nu0, that means say this is your nu. Now you reduce the energy. What will happen? You see, if you reduce the energy, say 9, then one part is utilized to coming out from the metal surface 8. The remaining part means is 1. 1 would be the kinetic energy. Now you reduce further the incident photon, the energy of the incident photon, say 8. Now your new incident radiation having energy 8, then part of its energy is utilized to coming out from the metal surface. So this 8. The remaining part means 0. So kinetic energy associated with the electron using this radiation having energy 8 is 0, because all of its energy is used to utilize for coming out from the metal surface. So there is no amount of energy remaining with the electron to have kinetic energy. But if you reduce the incident energy further, means say 7, then that energy is not sufficient to liberate electrons from the metal surface, because the electron need minimum 8 amount of energy to liberate from the metal surface. So this is called work function. So there is a minimum energy which is required to coming out from the metal surface, and metal to metal it varies. For example, I am using a special type of metal which have a work function 8. These are hypothetical. We are we are using this 879 for to understand the physics. Okay. So this is 8. This is 8. Suppose we are using the metal suppose which have a work function 8. So if you use a photon having energy less than 8 means 7. So this much energy is not sufficient to liberate the electrons from the metal surface because the electron need 8 amount of energy to liberate from the metal surface, but your incident photon have energy less than 8. So this frequency or this radiation is not sufficient to liberate the electrons. That means this radiation is not sufficient to show the photoelectric effect. So to have photoelectric effect from the metal surface, amount of incident radiations must have a specific a minimum value. For in this case, in this hypothetical case, if your incident photon have energy 8, then that complete energy is utilized to liberate the metal surface, and your kinetic energy becomes equal to 0. At least your electron emitted from the metal surface having 0 kinetic energy. At least your electrons are able to liberate from the coming out from the metal surface, having they coming out and they become raised over here. If there is a positive potential, then for that positive potential, a positive plate attract the electron and they reach over here and complete the cycle so that you get a current. Okay, so amount of energy, there is a minimum amount of energy required, and that energy actually is called threshold energy, which is minimum energy to show the photoelectric effect, and the frequency associated with the energy is called the threshold frequency, starting frequency. That means this amount of frequency is required. At least this amount of frequency is required. Suppose this is your threshold frequency, so this amount of frequency is required. If you fall the radiations, if you expose your metal surface to the radiations having frequency nu 0, what will happen? If you expose your metal surface having to the radiations having frequency nu 0, then what happened? When nu is equal to nu 0, then your kinetic energy becomes equal to 0. Okay, so yeah, the hypothetical case, if your energy is 8, then your kinetic energy is 0 because all of the energy is utilized to overcome the metal surface. That means all of the energy is utilized to work function of the metal. So when nu is equal to nu 0, your kinetic energy is equal to 0, and this is the definition of the threshold frequency. So what is the threshold frequency? Threshold frequency is the minimum frequency required to liberate electrons having kinetic energy is equal to 0. Okay. Now putting these values over equation 1, so H now nu is equal to nu 0, W0, then kinetic energy becomes equal to 0. So this gives us this expression. This is the work function of the metal surface, W0, work function of the metal surface. Okay now, for different metals, your work function is different, your threshold frequency is different. So putting this value over here, your equation 1 is reduced to a new form. Now your equation 1 becomes H nu is equal to W0. Now W0 is defined as H nu 0 plus kinetic energy. So this is now your new modified Einstein's equation. This is also Einstein's equation. Equation 1, this is equation 2. This is a new form of the Einstein equation. Okay. Okay. Now another form. So what happened up to this? So you have this kind of chamber where you have metal surface. This is actually metal surface. This is anode, and this is called cathode. This is connected with the negative terminal of the potential, positive, negative, positive, negative, positive, negative, positive. Okay, then this is connected over here, and radiation is now incident on the metal surface, so that electron ejected because frequency is new, energy of the photon is h nu, and electron ejected from the metal, and they move to the anode. We get a current right here. So nu is the incident frequency of the photon, so incident energy of the photon is h nu. Simple. Nu zero is the work function, so energy utilized to overcome from the metal surface is h nu 0. So difference of energy h nu minus h nu 0 is called kinetic energy. Okay, so it has suppose nu is greater than nu 0, so nu is greater than nu 0, so electron has kinetic energy. So these electrons have kinetic energy. Suppose if you not connecting any potential over here, still you will get some current. Why? Because electron, they are coming from the metal surface, have kinetic energy. That's why electron will move to this plate and reach over here. As electron from this cathode to anode traveled from cathode reached to anode, as a result from anode, then the electron moving this through the wire this side and coming to this plate. That means the complete path of the electron is observed, so that current will flow in the opposite direction. You will get a current because electron coming out from the cathode have associated with some kinetic energy, and that kinetic energy is sufficient to reach anode without having any potentials over here. That means they need no attractions to complete its path from cathode to anode. They complete this path without helping any potentials. They utilize its own energy, kinetic energy. They have some kinetic energy, so that they complete, they travel from cathode and move to anode. And when they move to anode, then automatically they flow through this wire and complete the cathode, again coming to cathode. So there is a complete path over here without any potential, so there is a current associated with the motion of the electron. And this is called the current without potentials. Why? Because the electron coming out from the metal surface have associated with some kinetic energy. Okay. Now, if you connected a reverse voltage over here, that means this side now becomes negative and this side now becomes positive. Then the electron which are emitted from the cathode having kinetic energy Ek given by this equation, and then due to the kinetic energy they try to move over there, but due to the negative potential of the anode, this negative potential gives the repulsive force, so electron now loses kinetic energy. It loses its kinetic energy because it now moves against the repulsion. Okay, it now moves against the repulsion. If suppose this voltage is V1, then when electron coming out from the cathode and reach anode, utilize losses energy EV1. If this loss is less than its initial kinetic energy, if this loss is less than the initial kinetic energy, then electron can reach up to anode, produces current. Now you increase this voltage to V2. Suppose this is the now you increase from V1 to V2, increase V1 to V2 reverse voltage. Now this voltage, when electron, again this voltage produces a repulsive force to the motion of the electron because there is a negative potential. But again, if the electron moving from this plate to this plate, then amount of energy it loses, that it EV2 charge into potential difference. If now this potential difference is less than its kinetic energy, then again it can reach up to and produce a current over there. Our intention is to stop the motion of the electron or this current. Our intention is to stop the motion of the electron to the motion of this electron, that means the reaching of the electron up to anode, to stop the current. When the electron cannot reach up to anode, then automatically current will stop. So we increase the potential further, say Vs. Now that potential is sufficient because electron when moving against this potential, it loses its kinetic energy. Electron when moving, just try to understand the physics. Electron is moving against this potential because it is a negative potential. This plate is now negative. So electron is moving against this potential because this negative potential given a repulsive force to the motion of the electron. But still electron utilizes its kinetic energy and it move and loses its kinetic energy. And when it reach over there, just over there, it loses its all kinetic energy. So ultimately, it cannot reach up to anode because it has less energy. Because suppose to reach from there to there, it need energy 5, and it has initial kinetic energy 4.9. So 4.9 is utilized to reach up to this point, but it needs amount of energy 5 to work up this potential, but it has less than 5, so it cannot reach up to anode. So automatically current stop. So to stop the current, we use potential Vs. So amount of energy when electron move against this potential is EVs. This is work done against the potential. If this work done against the potential is at least equal to its initial kinetic energy, then we can say the electron will not reach up to anode and current will stop. That's why this potential is called stopping potential. This Vs is called stopping potential because it stops the electron reaching up to anode and ultimately current stop. So that's why this potential is called stopping potential. Okay, so Vs, again you have to remember this potential is actually negative potential. Okay, now the anode actually our concept is anode is positive and cathode is negative. Our concept is that anode is positive and cathode is negative. Over here anode is positive and cathode is negative, but to stop the electron you have to use anode is negative, cathode is positive. So when you define the stopping potential, you have to mention this configuration. Okay? Now when a negative potential is applied to the anode with respect to the cathode, in this fashion, when a negative potential is applied with the anode with respect to the cathode such that there is no current associated in the outer circuit or in the output circuit, in the external circuit, this external circuit, there is no current associated with the external circuit, then that minimum potential is called the stopping potential. How does this stopping potential utilize? Actually, this stopping potential associated an energy associated with the stopping potential is EVs, and that energy is actually utilize the kinetic energy of the it losses the kinetic energy, initial kinetic energy of the emitted electron, so that it cannot reach up to anode. Just before anode, it losses all kinetic energy, so there is no electron to reach up to anode. There is no current in the external circuit. Okay, so putting this value over here, So our Einstein equation now becomes h nu, putting the value in the equation 2, h nu is equal to h nu 0 plus E into Vs. So this is our new modified form of the Einstein's photoelectric effect. So there are three fashions of the three forms of the Einstein equation. It is fundamental h nu is equal to Wj plus Ke. Now then this h nu is equal to h nu 0 plus kinetic energy Ek. Now then this h nu is equal to h nu 0 plus EVS. Okay, h nu is equal to h nu 0 plus EVS. Okay. So EVS is h nu minus h nu 0. So suppose this is your threshold frequency, and if the incident radiations have a frequency this, then you need a stopping potential Vs. If the incident frequency have a higher potential frequency than this, then you need higher stopping potential. So more the difference between mu and nu 0, more would be the stopping potential. Okay, na? More the difference mu and nu 0, because that difference is actually utilized as a kinetic energy. So more the difference, more the kinetic energy electron, to stop the more energetic electron to stop the more energetic electron up to reach anode, we have to use more stopping potential, more negative potential with the anode. So this is your equation. Now divide by E, so h by E into nu minus h by E into nu 0. So this is an equation. You can easily draw a graph. Vs is equal to h by E into nu minus h by E into nu 0. So this is an equation. Now you can draw the graph of this equation. Okay, na? How? So let's start over here. Vs is h by E into nu minus h by E into nu 0. So you can draw along x-axis. Along x-axis you put frequency. Along y-axis you put stopping potential. So when nu is equal to nu 0, when nu is equal to nu 0, when nu is equal to nu 0, what will be the Vs? Remember Vs kota hobe? When nu is equal to nu 0, what will be Vs? When mu is equal to nu 0, what will be the value of Vs? Dipti, tell me, when nu is equal to nu 0, what will be the value of Vs? Are give the ball, anyone please? When nu is equal, পরিষ্কার দেখা যাচ্ছে, when nu is equal to nu 0, Vs is equal to 0. When nu is equal to nu 0, so this is your nu 0. And then Vs is equal to 0. There is no Vs, there is no height. Okay, and when Vs is equal to 0, what is nu? Oh, sorry. And when nu is equal to 0, when nu is equal to 0, then what is Vs? What is the value of Vs? Minus h by E into nu 0. Okay, na? When nu is equal to 0, then Vs is equal to minus h by E into nu 0. Okay. When nu is equal to nu 0, Vs is equal to 0. This is number 1. And when nu is equal to 0, Vs is equal to minus h by E into nu 0. Okay, na? This is nu. When nu is equal to nu 0, putting nu is equal to nu 0 over here, Vs is equal to 0. When nu is equal to 0, Vs is equal to minus h by E into nu 0. Okay? This is a negative potential. This is negative potential. Suppose this is your minus, this is your h by E into nu 0. This side is positive and this side is negative. So this is negative. So in this side, so this is h by E into nu 0, and this is the nu 0. Okay, connecting these two points, joining these 2 points, you will get a straight line. You will get a straight line. Okay, you will get a straight line. This is the equation of this graph. This is the graph of this equation. This is the graph of this equation. Okay. So this is point A. This is point B. This is O. So OA is how much? OA is nu 0. And OB is how much? OB is H by E into nu 0. From the graph, you can easily calculate the Planck constant. From that graph, you can easily calculate the Planck constant. How do you calculate Planck constant using the graph? Here, let's see Planck constant using the graph. How do you calculate Planck constant using the graph? Suppose this is slope of the graph theta. If this is theta, then this is also theta. Then tan theta is OB by OA. Okay na? OB is H by E nu 0. OA is only nu 0. Nu 0 nu 0 cancel. So that is equal to H by E. So H is equal to E tan theta. So from the slope of the graph, you can easily calculate the Planck constant. It is the question. Okay. So this is a question, very important question. This is many times comes in the board exams. How the questions comes in the board exams. So write down the Planck Einstein equations. Then draw a graph between stopping potential and incident frequency of the photon. And from that graph, explain how do you calculate the Planck constant of the Planck constant. So this is all about the Einstein's equations. So first you have to write H nu is equal to H nu 0 plus EVS. Okay, na? Then EVS is equal to H nu minus H nu 0. Then VS is equal to H by E nu minus H by E nu 0. Directly you could not write this equation. First you write the Einstein's equation, then convert the equation, then ultimately you can come to this equation. Then along this is Y, this is X, this is Y, this is X, this is Y. So this is H by E, some constants say M. Along this is nu is along X, so this is X, and this is C minus C. Okay, so this is Y is equal to Mx minus C. So this is the form of the equation. You will not have to write down this equation. I just write down to understand why this equation actually gives you the straight line. Actually, along Y you put Vs, and along X you put frequency. That's Vs is Y and frequency is X. So this is Y is equal to this is a constant M X minus this is another constant C. So this is Y is equal to Mx minus C. So this is the equation of the straight line. So to draw the straight line, we need 2 points. First is nu is equal to nu 0. Nu is equal to nu 0. Vs automatically 0. So this line, on this line, there is potential Vs is equal to 0. That's why this is nu 0, for which Vs is equal to 0. Second is nu is equal to 0. That means along this line, this is frequency is 0. Along this line, Y is 0. Along this line, X is 0. So along this line, Y is 0. Y is Vs. Vs is 0. When Vs is 0, nu is equal to nu 0. So this is called threshold frequency. So this much frequency is called threshold frequency. Along this line, this is Y line. Along Y, X is 0. So putting X equal to 0 means nu is equal to 0. You will get the value of Y for nu is equal to 0. That means X is equal to 0. This. So this is your, since this is negative, so this is the downward side. So this is the point B, point A. So joining these 2 points, we get a straight line. So this is a straight line. Actually, this is the equation of the straight line. Actually, this graph is actually represented by this equation. From that graph, we have OA is equal to OA is equal to nu 0 and OB is equal to H by E into nu 0. And this is a slope theta. Theta is the angle, and tangent of the angle gives you slope. Tangent of the angle gives you slope. So this is perpendicular, this is base. Tan theta is equal to perpendicular by base, OB by OA. So OB by OA. OB is H by E into nu 0 and OA is only nu 0. So nu 0 cancel. We have H by E. So H is equal to E tan theta. So this is all about the process from the equations or from the graph. We calculate the Planck constant. Okay. Okay. So